Right now, all around you, something invisible is happening. Electromagnetic waves are racing through the air, carrying signals to your phone. The Earth is orbiting the sun without ever touching it. A simple magnet can move iron across empty space, pulling it without any visible connection. And here's the astonishing part. We can calculate all of these interactions with extreme precision. We can predict the tides, the paths of satellites, the motion of electrons, even the way light bends around objects. But if you go beyond the what and start asking about the how, things get truly strange. It's easy to describe what happens. The iron moves when the magnet approaches. The Earth stays in orbit. Electrons interact with photons. We can measure all of it. But the question that has haunted physicists for centuries is this: how does one object affect another when there is literally nothing between them? There's empty space separating the magnet and the iron, the Earth and the sun, the moon and the Earth. And yet, influence passes across that emptiness. What travels through the void? What carries the force? This problem troubled some of the greatest minds in science. Isaac Newton, for example, described gravity with exquisite mathematical precision. He could predict the motion of the planets and the moon, explain tides, and describe countless other phenomena. Yet he admitted that he had no idea how gravity worked at a distance. How does the sun reach out and pull on the Earth? What crosses the space between them? For centuries, this question was avoided because it was uncomfortable, even unsettling. The simple intuitive picture of reality, that objects only act when they touch, was crumbling. Consider the difference between direct contact and action at a distance. Push a book across a table. Your hand touches it. The interaction is immediate and obvious. You can see and feel it. That's contact. It makes intuitive sense. But now take a magnet and a piece of iron. Hold them apart with a gap of several inches. Nothing touches. There's literally empty space between the two objects. And yet the iron moves. Something clearly happened. The iron did not spontaneously decide to slide toward the magnet. Something crossed that empty space. For centuries, the mechanism of this action was a mystery. The old view of the universe was simple. One object reaches out, influences another, done. But when you slow it down and think carefully, the picture starts to break. How does the magnet know the iron is there? Does it send a signal? If so, through what medium? At what speed does the signal travel? Or does the effect appear instantaneously, as if the influence is everywhere at once? These questions are not trivial. They strike at the heart of how we understand reality. Gravity presents the same puzzle. Every object in the universe pulls on every other object. The sun pulls on Earth. The Earth pulls on the moon. Even your body exerts a tiny gravitational pull on every object nearby. But through what mechanism does this happen? Is there a field that carries the influence, or does the effect leap across space with no intermediary? For centuries, scientists didn't know. They had precise formulas, precise predictions, but no explanation of the underlying mechanism. The answer came gradually, and it changed everything we thought about empty space. Physicists realized that space itself is not empty. It never has been. What appears to be a void is actually a medium filled with fields, invisible structures that carry forces and information. Electromagnetism, gravity, and other fundamental interactions operate through these fields. The magnet does not reach across empty space magically. Instead, it creates a magnetic field that permeates the surrounding space. The iron moves because it interacts with that field. Likewise, gravity can be understood as a curvature of space and time. Massive objects bend the geometry around them, guiding the motion of other bodies. This shift in understanding was revolutionary. Suddenly, empty space was no longer a simple backdrop. It became an active player, a canvas filled with invisible structure, a medium through which forces operate. Electromagnetic waves, for instance, are not just effects traveling through nothing. They are disturbances in the electromagnetic field, carrying energy and information across space at a fixed speed, the speed of light. Light itself is a vibration of the electromagnetic field, a moving pattern that propagates through this otherwise invisible medium. Even more startling is the way these fields interact. the Earth orbiting the Sun, electrons moving through a wire, magnets pushing iron. All of these effects can be described and predicted using the mathematics of fields. We don't need to invoke mysterious action at a distance. Instead, we understand the mechanism. Objects create changes in the field, and those changes propagate, influencing other objects according to well-defined laws. And yet, when you first encounter this, it feels profoundly weird. The space between the Sun and Earth is vast and seemingly empty, yet it is alive with structure, energy, and rules. This insight, fields, and the structure of space was not just a small correction to Newtonian mechanics. It rewrote our understanding of reality. It explains why magnets move iron, why the Earth orbits the Sun, and even why electromagnetic waves can travel across space to carry data to your phone. It shows that empty space is anything but empty. It carries signals, transmits forces, and contains the architecture of the universe. The story doesn't end there. Quantum mechanics adds another layer of strangeness. In the quantum view, the vacuum is never truly empty. It is teeming with fluctuations, brief appearances and disappearances of virtual particles, energy popping in and out of existence. Even in the void, there is activity, there is structure, there is interaction. This is why physicists say the question, what crosses empty space, has an answer. Fields, disturbances in fields, and the underlying fabric of space itself. The implications are profound. Forces are no longer mystical. They are structured, measurable, and predictable. Yet space is not simply a backdrop for events. It is an active participant. The magnet, the iron, the Earth, the Sun, photons, electrons, they all interact through the medium of space, obeying laws that we can measure with astonishing precision. And at the same time, the nature of this medium is so strange, so far removed from everyday experience that it challenges our intuition. In essence, what we perceive as empty space is actually a dynamic, invisible, and structured environment, capable of transmitting forces, guiding motion, and carrying information. The phenomena we take for granted, the orbit of the planets, the behavior of magnets, the propagation of light, are all expressions of this deeper reality. Physics has given us the tools to measure it, calculate it, and predict it, but the underlying mechanisms remain astonishingly counterintuitive. And that is what makes it beautiful. The universe is not a stage on which events simply happen. It is a complex, interconnected web in which empty space is filled with structure, forces are carried through invisible fields, and the apparent simplicity of the world masks layers of profound, elegant complexity. Isaac Newton himself, the guy who wrote down the law of gravity, was deeply troubled by this. He could calculate orbits perfectly, but he explicitly refused to speculate about the mechanism. He wrote that he feigned no hypothesis about how gravity actually worked across empty space. Think about that for a second. The man who could predict planetary motion with stunning accuracy, who gave us the equations that still work today, openly refused to claim he understood the underlying mechanism. He could calculate where planets would be, but he couldn't explain why gravity worked the way it did. It bothered him deeply. And here's the thing, this is crucial for understanding all of physics. Being able to calculate something is not the same as understanding it. You can predict where a planet will be in 100 years without knowing how the sun is actually pulling it. This tension runs through all of science, calculation versus comprehension, and it's about to crack open. The idea of a field was invented precisely to resolve it. But before we get there, hold on, because the solution requires us to question something even more fundamental to what do we actually mean by empty space. We usually say space is empty when there's no matter in it, no atoms, no dust, no air, just nothing. But is that really the end of the story? Here's a thought experiment. Imagine placing a tiny charged particle at some random point in space just sitting there. Now watch it. If it suddenly accelerates, if it starts moving, then something must be acting on it, but you didn't put another object nearby. There's nothing visible touching it. So what's happening? The old answer would be some distant object is mysteriously pulling on it through empty space. But here's the new answer, the one that actually makes sense. The space at that location is in a certain condition. Not empty, not neutral, but in a specific state that determines what happens to anything placed there. This is the first key idea of a field. It's subtle, so let's be careful. A field is not a thing sitting in space like a rock or a chair. It's a description of the state of space itself. Think of it this way. At every single point in space, everywhere continuously, you can assign a value, a number, a direction, or both. That value tells you what would happen if you place the right kind of object there. For an electric field, that value tells you the force a charge would feel. For a gravitational field, it tells you the acceleration a mass would experience. And here's the wild part. You don't need the object to actually be there for the field to exist. The field is already there, quietly, everywhere waiting. Now this might seem like a subtle semantic shift, like we're just playing word games. But watch what happens when you fully embrace this idea. Instead of saying the sun pulls the earth, you say this: the sun alters the gravitational field of space around it, and the earth responds to the field at its location. Notice what just happened. The interaction is no longer some mysterious long-distance handshake happening instantaneously across millions of miles. It becomes local. The earth only responds to what's happening right where it is. And this matters enormously because nature seems to absolutely insist on locality. Things influence nearby things. Any influence takes time to propagate. Information can't travel infinitely fast, and a field allows exactly that. Here's where it gets interesting. If the sun were to suddenly vanish, strange thought, but stay with me. The change in the gravitational field wouldn't be felt instantly everywhere. The Earth wouldn't immediately fly off into space. Instead, that change would move outward through space at a finite speed. Space itself would adjust point by point like ripples spreading across a pond. This wasn't some wild speculation. This was forced on us by experiments. Historically, this idea didn't just appear fully formed. It emerged slowly, pushed forward by people who were trying to make sense of experiments that absolutely refused to fit the old picture. Take electricity. Early experiments showed forces between charges that looked eerily similar to gravity, stronger when objects are closer, weaker when farther apart. You could have stopped there and said, fine, another action at a distance force. Case closed. But the experiments kept getting weirder. Moving charges produced magnetic effects. Now draw arrows showing those directions. You've just drawn a picture of a magnetic field. And notice something crucial here. The field is not the magnet. The magnet is just the source. The field exists everywhere around it, with its own pattern, its own structure. You could remove the magnet and ask, what would a compass do here? The field gives you the answer. But hold on. This changes everything about how we think about reality because you can do this with anything. Think about temperature. A room has a temperature at every point. You don't need a thermometer at every location to talk about the temperature field. The thermometer merely reveals what was already there. In the same way, a charged particle or a mass is like a probe. It tells you what the field is doing at that point. This analogy removes some of the mystery. We're already used to the idea that space can have properties, hot here, cold there. A field simply extends this idea to forces and motion. But now comes the deeper question, the one that separates physics from philosophy. Is a field just a mathematical convenience, or is it something physically real? At first, many scientists hoped it was just bookkeeping. Instead of calculating forces between dozens of objects, you calculate a field once and then see how things respond to it. Steady, efficient, useful. But over time, experiments began to suggest something far more radical, something that would force us to take fields seriously as physical entities, not just math. Fields can carry energy. They can carry momentum. They can vibrate. They can even exist in regions where there are no particles at all. And then came the breakthrough that sealed it. Light itself turned out to be a wave in the electromagnetic field, an oscillation propagating through space. No charges required once it's created, just the field vibrating, carrying energy from one place to another. This was a remarkable realization. What we once thought of as nothing, empty space, turned out to be capable of supporting waves, storing energy, transmitting influences. Space wasn't a passive stage where physics happened. It became an active participant. But this is where it gets uncomfortable. At this point, you might be thinking, okay, fine, fields exist, but what are they? What are they made of? And this is where we have to be extremely careful, because history is full of wrong turns caused by insisting that every new idea must resemble an old one. People once imagined a substance called the ether, an invisible material filling all of space, vibrating to carry light waves the way air carries sound. It made intuitive sense. Waves need a medium, right? Water waves need water. Sound waves need air. So light waves must need something, except they don't. That idea, the ether, turned out to be completely unnecessary, deeply misleading. Experiments proved it didn't exist. So here's the uncomfortable truth. The field doesn't need to be made of anything in the ordinary sense. It's not a substance. It's not a material. It's a fundamental entity. Asking, what is a field made of, might be like asking, what are numbers made of? It's possibly a category error, or maybe it's a question we just can't answer yet. Either way, what matters in physics is not what the field is in some deep philosophical sense, but what it does and how it behaves. Physics doesn't progress by naming the ultimate substance of reality. It progresses by discovering reliable rules that connect observation. So let's focus on what fields allow us to do. They replace mysterious distant influences with local interactions. They describe change propagating through space at finite speeds. They unify seemingly different phenomena, electricity, magnetism, light into a single framework. And they force us to rethink what we mean by nothing. But here's where it gets truly strange. If fields exist everywhere, even in empty space, then the universe is never truly empty, ever. Even in the darkest void between galaxies, even in a perfect vacuum, fields are there, present, active. And if particles are just things that respond to fields or sometimes excitations of fields themselves, then maybe particles aren't the most fundamental actors after all. This brings us to the edge of a much bigger idea, one that completely changes how we think about matter, forces, and reality itself. Because if space can have fields, and fields can carry energy and interact, then what exactly is a particle? And could it be that what we call objects, solid, definite things, are merely special behaviors of something deeper and more continuous? That question isn't just philosophical. It reshaped all of physics in the 20th century. And once you take it seriously, you can never look at empty space or at objects quite the same way again. So before we go deeper, here's the question I want you to hold on to. If forces don't act across space directly and space itself can carry influence, energy, and structure, then is the field more fundamental than the things we thought were doing the acting? If space can carry structure, energy, and influence, if it can have a condition at every point, then we're forced to reconsider something we usually take completely for granted, that objects are the basic ingredients of the universe. This is how we instinctively think. We imagine a world made of little bits of matter, particles flying around, bumping into each other, pulling and pushing through forces. Fields in this picture are secondary, convenient, useful, but not really real in the same sense as particles. Now here's the part that'll flip your understanding upside down. Modern physics quietly reverses that entire picture. Instead of particles creating fields, it turns out to be far more accurate to say that fields come first. And particles are what we observe when fields behave in certain localized, quantized ways. That's a strong claim, so let's not rush it. Let's see how nature pushes us there step by step. Start with something familiar, waves on water. You don't think of a wave as a thing separate from the water. It's a pattern, a motion of the water. If you ask, what is this wave made of? The answer is simple, water. But the wave itself isn't a chunk of water traveling across the ocean. The water mostly stays where it is. The pattern moves. Now imagine you see a sharp, localized ripple moving across the surface. It's tempting to treat it like an object, a thing moving from here to there, but it isn't. It's a temporary structured behavior of a continuous medium. Fields behave in a nearly similar way. An electromagnetic field fills space. When it oscillates in a particular pattern, we call that light. When that oscillation is localized and quantized, when it can only exist in discrete packets, we call those packets photons. But the underlying entity is still the field. So when you see a photon detected at a point, when a sensor clicks, when your eye registers light, what you're witnessing is not a tiny billiard ball arriving there. You're seeing the electromagnetic field interacting with matter in a discrete way. This isn't interpretation. This isn't philosophy. This is forced on us by experiment. Because in quantum physics, particles do not behave like solid objects moving along definite paths. They spread out. They interfere with themselves. They behave like waves until suddenly they don't. The only description that consistently works, the only one that matches what we actually observe, is one where the fundamental entity is a field defined everywhere. And what we call a particle is an excitation of that field. Every type of particle corresponds to its own field. There's an electron field, a quark field, a neutrino field. Even empty space, by this account, is not empty. It's a collection of fields in their lowest energy states. This is why the word field becomes unavoidable. You can try to avoid it, you can resist it, but the mathematics and the experiments won't let you. But here's where it gets even stranger to a field is not just a static background. It's dynamic. It can change with time. It can interact with other fields. And most surprisingly, it can fluctuate even when nothing seems to be happening, even in its lowest energy state, what we'd call a vacuum. A quantum field is not perfectly still. It jiggles, not because of external disturbances, not because something's shaking it, but because the laws of nature forbid it from being completely motionless. This isn't noise. This isn't an imperfection in our measurements. It's intrinsic. So when we say vacuum, we don't mean nothingness. We mean the ground state of all fields, a condition with structure, energy, and consequences. And this explains something that would otherwise be deeply puzzling, how particles can appear and disappear. Energy supplied to a field can cause it to produce excitations, particles out of what we would have once called empty space. Later, those excitations can vanish back into the field. Nothing is being created from nothing. The field was there all along. Notice how radically different this picture is from the old mechanical worldview. Instead of a universe built from tiny solid pieces, little billiard balls bouncing around, we have a universe built from continuous entities with discreteness, emerging only in how they're excited and observed. At this point, it's natural to feel a little uneasy. Fields are everywhere. They're invisible. They can't be picked up or pointed to in the ordinary way. And yet, we're being asked to treat them as the most real things there are. So how do we know we're not fooling ourselves? Because fields do something very important. They make precise predictions that no object-based theory can replace. They tell us exactly how fast influences propagate. They explain why electromagnetic effects travel at the speed of light. They predict new phenomena, waves, radiation, interference patterns that are later observed with extraordinary accuracy. They unify forces that once seemed completely unrelated. And perhaps most tellingly, when we try to remove fields from our theories and talk only about particles interacting directly, the mathematics becomes inconsistent or meaningless. Fields aren't an optional extra. They're the language nature uses. But there's one more piece to this puzzle. Let's return briefly to gravity because it completes the picture in the most elegant way. Gravity was the first force we learned to describe mathematically, but it was the last to fully accept the field viewpoint. For a long time, gravity looked like a simple pull between masses. Neat, predictable, done. But eventually, experiments forced a deeper interpretation. Instead of a gravitational force acting through space, we now describe gravity as a property of space itself, its geometry. Mass and energy don't just sit in space. They change the structure of space and time, and objects move in response to that structure. Once again, the influence is local. An object reacts only to the condition of space where it is. In this sense, gravity isn't even a force in the traditional meaning. It's the curvature of space-time itself. Mass and energy tell space-time how to curve, and that curvature tells objects how to move. You could describe this with a field, the metric field, but it's fundamentally different from other forces. Here the arena itself is dynamic, so whether we're talking about electricity, magnetism, light, or gravity, the message is the same. Space is not a passive void, it has properties. It responds, it evolves, and now we reach the turning point. If fields are everywhere, and particles are excitations of fields, then the universe is less like a machine made of parts, and more like a continuously active system structured by rules rather than pieces. This doesn't make reality vague or fuzzy. On the contrary, it makes it more precise. Fields obey exact equations. Their behavior is constrained. They don't do whatever they like. They do what the laws demand. But it does change how we should think. Instead of asking what objects are interacting here, we ask what fields are present and how are they configured. Instead of asking what forces are acting across this distance, we ask how does the field change from point to point. And once you adopt this viewpoint, a remarkable thing happens. Many mysteries stop being mysteries. They become consequences. So here's the question that naturally comes next, and it's the one we can't avoid if we want to go deeper. If the universe is fundamentally made of fields, not objects, if particles are just special disturbances of something continuous, then what does that say about matter identity and the very idea of things existing at all till we began with a simple discomfort? Objects seemed to influence each other across empty space, and no one could quite explain how that discomfort turned out to be a clue. By following it carefully, without rushing, without hiding behind formulas, we were led to a quiet but radical idea. Space itself is not nothing. It has structure, it has conditions, it can carry influence. A field is our name for that structure. It's not a trick for calculation. It's not a ghostly substance floating between objects. It's the way nature organizes cause and effect locally. At every point in space, something is defined, and objects, when they appear, respond only to what's happening where they are. No mysterious reach across the universe. No instant messages through nothingness. It is simply space behaving in a specific way at every point. Once that idea is accepted, the old mental picture falls apart. Particles are no longer tiny, solid objects reaching across space to tug on one another. Instead, they are events, localized, quantized excitations of deeper underlying fields. Matter is no longer the fundamental layer of reality. It emerges from something more basic. What we once thought of as solid things turn out to be stable patterns in those fields. This shift does not make the universe feel abstract or unreal. In fact, it makes it more internally consistent. The same framework that explains how magnets attract and how light travels through space also explains why matter has mass, why atoms hold together, and why forces act the way they do. Different phenomena that once seemed unrelated turn out to be expressions of the same underlying structure. In this view, space is not an empty stage with objects moving across it. Space itself carries properties. It can vibrate, bend, store energy, and transmit influence. What we call particles are simply the smallest detectable units of these behaviors. They are not little beads flying through nothing. They are localized behaviors of space itself. Once you see the universe this way, everything fits together more cleanly. Forces are no longer mysterious actions at a distance. Motion, interaction, and structure arise naturally from how fields behave. Matter, energy, and radiation become different faces of the same underlying reality. The universe stops looking like a collection of separate parts and starts looking like a single interconnected system governed by consistent rules. This perspective does not remove wonder, it deepens it. What appears solid is actually dynamic. What seems empty is full of structure. And what once looked like disconnected phenomena are revealed to be part of one coherent framework, unfolding everywhere at once.